All right, so section 21.4 deals with Claisen condensation. It's kind of a cool reaction. It says here that esters can undergo these reversible condensation reactions that you see here, and we call it a Claisen condensation. And keep in mind that condensation, the word condensation in chemistry doesn't always mean the loss of water, right? We think of condensation on a glass of, ice water on a day like this. Well, what's going to condense on the sides of the glass? It's going to be water. But a condensation reaction in organic chemistry can mean the loss of a small molecule, because you see that we didn't lose water here. What we actually lost is ethanol overall. We ended up losing ethanol in this case. So we're taking this ethyl ester. So this is ethyl acetate. That's the name of this ester here. And you can just practice your nomenclature along the way, right? So we have ethyl acetate. We're taking that and we're treating it with sodium ethoxide. Well, what do we know is that if we're treating it with a base like sodium ethoxide, the pKa of ethyl acetate, it's got a pKa of around 25. So what we're going to have in the solution is we're going to have some of the ethyl acetate, but we're also going to have some of this, right? We're going to end up with some of this deprotonated form here, which can then do a nucleophilic attack like this. So it's essentially like a nucleophilic acyl substitution between two esters, okay? Anyhow, so we end up with the Claisen condensation product, and we call this a Beta-Ketoester, right? So here's our ester right here, and if you look at the alpha carbon after the carbonyl of the ester, you can see that on the beta carbon there's a ketone, so that's why we call it a Beta-Ketoester. So a Claisen condensation, like I tried to explain, is really nothing more than a nucleophilic acyl substitution, except our nucleophile is the enolate of the ester, and our electrophile is the ester itself. Okay, so we end up with both of those in the solution when we treat it with a base like sodium ethoxide. So let's take a look at the mechanism. And I'm sure that you would all be able to figure this out on your own, that you're going to do a proton transfer to make what? You've produced the enolate, right? This is your enolate right here, but you also have some of the ester. Okay, well, if I have some of the ester, these are the arrows that I tried to draw on the previous slide, right? So we have our nucleophilic attack, we form a tetrahedral intermediate right here, and then we lose the alkoxide, whether it's, ethoxide, methoxide, whatever, we lose that leaving group. Now notice that all these steps are in equilibrium, okay? You see that all of those steps are in equilibrium. But here's the driving force of the reaction, is you end up forming the Beta-Ketoester, but since you're in a basic solution, you guys remember that the pKa of this proton is actually pretty low. It's going to be, 10 or less. And so it's acidic enough that if you have some alkoxide kicking around, it's going to rip that off, and then you end up with a doubly stabilized enolate, right? And everybody here should be able to draw both resonance structures. You should be able to draw this resonance structure, and you should be able to draw this resonance structure like that. And so we form that doubly stabilized enolate, and look at this equilibrium here. You see that it actually lies to the side of the doubly stabilized enolate. Why? Because that is the driving force for this reaction. If you're wondering, what makes this reaction tick? What makes it happen? Well, the reason it happens is because when you're in the basic environment, you form the doubly stabilized enolate. That pushes the reaction forward, okay? But the reaction isn't over, right? You see, if you go back here, that it's a two-step process. The first step is treating it with the base. You end up with the doubly stabilized enolate at the end, but then you have to protonate it. So you have to throw in some acid. So here's what we do. We end up with the doubly stabilized enolate. You put in some acid, you do a proton transfer, and you're done. There you go, your Beta-Ketoester. Again, this is a beta. Here they use all one word. I mean, sometimes you see it in two words like that, but we'll just call it a Beta-Ketoester, like that. So whenever you see a Beta-Ketoester in organic chemistry, you can always think of a Claisen condensation. Sometimes if you're the kind of person that likes to peruse the internet, you might hear it called a Claisen reaction, but I went to school with a Scottish guy, and he said, it's obviously Claisen, Anyhow, so that's why, the fact that you form that doubly stabilized enolate, that's why it's a two-step process. So step one is going to be your alkoxide, okay, whether it's ethoxide, methoxide, what have you. And the second step is to treat it with aqueous acid in your Claisen condensation. Well, there are some limitations to the Claisen condensation, right? What's organic chemistry? Well, It's many things. So one of the things it is learning the rules and then learning the exceptions to those rules. So limitations to the Claisen condensation. In order to form that doubly stabilized enolate, your starting ester has to have 2 alpha protons, right? If you go back here and you look at the first example, I mean, you can see that this ester has 3 alpha protons, right? 1, 2, 3, like that. But you've got to have a minimum of 2, right? Because you end up ripping off the first one in the first proton transfer to make the enolate, but then you rip off a second one when you form the doubly stabilized enolate. So you've got to have at least 2 alpha protons, okay? The second one, it says hydroxide can't be used as a base, okay? You've got to have, you know, some kind of alkoxide, like ethoxide, methoxide, whatever, okay? Why? Because if you have hydroxide as your base and you're just treating it with an ester, well, then what's going to happen is you're just going to do a saponification reaction. That's what's happening here. It says ester hydrolysis. Well, what's an ester hydrolysis in base? It's esterification. So that's essentially what's happening here. Saponification is what I meant to say. This is saponification, right? And what's the driving force here? You look at the first step, the nucleophilic attack. It's in equilibrium. The loss of leaving group. It's in equilibrium, but the last step when you form the carboxylate, that's not an equilibrium, is it? That's going to push the reaction forward, and all you're going to end up with is a bunch of carboxylate, and you will have destroyed all of your ester. Okay, so it's got to be an alkoxide base. Okay, it can't be a hydroxide base. Another one that's kind of interesting is that the alkoxide that matches the OR group of the ester has to match, or sorry, the alkoxide has to match the ester group is basically what it's saying here. Okay, so if you have an ethyl ester, okay, you wouldn't want to use methoxide. You would actually, so this is actually incorrect, what's shown here. You would actually want to use ethoxide, okay? So if we could do the Drake meme, right? Methoxide, no, right? Ethoxide, yeah, okay? The reason why is because if you use a different alkoxide base, or a base that's its alkoxide is different from this OR group over here, then you get a transesterification reaction, and then you've got a mixture, right? You'd have some of the ethyl ester and some of the methyl ester in this case. Well, that doesn't help you, right? You want to avoid that kind of stuff at all costs. So in this case, you end up with a mixture of products, which is always painful, right? Then you have to run TLCs and find ways to separate them and stuff like that. So again, if we go back here, if you're confused about that, if you're like, what does he mean by that exactly? Okay, it's simply this. You see how the OR group of the ester here is ethyl, right? This is an ethyl ester. That means you have to use ethoxide. If it was OMe, if it was a methyl ester, then you'd have to use methoxide. That's all it means, okay? And that way, even if transesterification, quote unquote, happens, and it's not technically wouldn't be transesterification, but if it did react, you'd still end up with the ethyl ester if you used ethoxide, okay? So that's another limitation. Well, we can also do what are called crossed Claisen condensations. So in the first Claisen condensation, we started with one ester, we treated it with an alkoxide base, and we ended up, you know, having it react with its enolate form, right? But there's also examples here of this crossed Claisen where we can use 2 different esters. Now, what would the criteria be for doing a crossed Claisen? Well, you remember we looked at crossed aldol condensations, right? And crossed aldol reactions, I guess, whether they were additions or condensations. Anyhow, one of the criteria is if one of the ester has no alpha protons. Well, that's certainly going to limit the number of products that you would have, right? You'd get much less products. Another option. So what I was just, if you're wondering why I'm pausing, the reason is I'm looking at my notes here, and there's something kind of interesting about this reaction. Let me just stop here and explain it to you. This is the kind of thing you probably wouldn't figure out, but I'll just tell you. In our textbook, like I have looked at the solutions manual. I do look at it from time to time. And he never uses this reaction. Or at least it says here, I couldn't find an example quickly where he used this type of cross Claisen condensation, where he used an alkoxide base. Okay, he almost always uses this, a directed Claisen condensation. Okay, so if you have, you know, two different esters that you want to react, he always uses LDA, okay, which is a directed Claisen. And the directed Claisen, I'll be honest, I worked with a gentleman who was an expert in directed Claisen addition, and it's analogous to a directed aldol addition, right? So what you do is you take the ester that you want to use the enolate, okay? You treat it with lithium diisopropylamide. Remember that? That's what LDA is. If you've forgotten what the structure is, I could draw it out for you here. So it's just you have two isopropyl groups on your nitrogen. It's got a negative charge, so that's LDA. It's a strong base. It's not a good nucleophile because it's too sterically hindered. So you take it, you treat it with LDA, and then what you would do is you would add this dropwise to this in solution. So you just add it, and it would react and form this, you know, it would form this intermediate, this doubly stabilized enolate super quickly. Okay. Again, what I'm saying is that I couldn't find an example in the book or in the textbook where he actually used this. Okay. Whenever he asks you to do a crossed Claisen condensation, he always uses LDA, and it just seems to be his favorite way of doing it, which is probably more common anyway. Well, you remember the intramolecular aldol condensation reaction that we looked at earlier today? Well, you can also do an intramolecular Claisen condensation. And when you do that, it's got its own name. It's called a Diekmann cyclization. I've actually heard it pronounced the Diekmann cyclization. I don't know. I'm pretty sure it's a German name. But the Diekmann cyclization. So you have two esters in the same molecule. Well, if you treat it with sodium methoxide, that means, let's say one of them gets converted to the enolate. I'll just draw a negative charge over here. Well, what's that going to be able to do? That's going to be able to act as a nucleophile, and you do a nucleophilic acyl substitution. So you end up forming a 1, 2, 3, 4, 5-membered ring, and there's the 5 atoms in the ring right there. Okay, and you know, this would be a good question to try drawing the reaction mechanism. Also, you can see that you're using sodium methoxide, right? You would end up with a doubly stabilized enolate because you have this proton here that's alpha to 2 carbonyls, and then of course in the last step you would treat it with aqueous acid to protonate that. All right. Anyhow, just like an aldol reaction, the Diekmann cyclization is only going to form either a 5 or a 6-membered ring. So if it's, you know, if there's any other option like a 4-membered ring or a 3-membered ring or a 7-membered ring or something like that, it's not going to happen. Okay, you're always going to be given an example where you form a 5 or a 6-membered ring. Well, with all that stuff in mind, let's practice drawing the products of a Claisen condensation, and I can show you some shortcuts that I use to draw these types of mechanisms. So first thing I do is, here's the only alpha protons that I have are going to be on this carbon. There's 2 of them. So I like to just do the deprotonation first, and then I draw the enolate like this, and then what I'll do is I'll redraw the molecule. So because I'm going to have some of the enolate in solution, and then I'm going to have some of the non-enolized form, or just the neutral form of the compound. So then what happens is I'm going to get a nucleophilic acyl substitution, essentially. So remember that you can't draw, you're not supposed to draw the mechanism of nucleophilic acyl substitution as being like this nucleophilic attack and then a loss of a leaving group like that. But that's essentially what's happening, okay? It's just that, okay? This nucleophilic attack and loss of leaving group. In fact, if you were to draw the product of these 2 arrows that I've drawn here, you would get the right answer, okay? But we know that technically what happens is you end up with a tetrahedral intermediate, then the negative charge in the oxygen comes down, makes the pi bond, and you lose the leaving group like that. So I told you earlier on in this class, and I don't remember exactly which day it was, but I said that sometimes organic chemists will draw an abridged version of the mechanism, where in our book we'll never do this, but what they do is this, is they'll say you'll break the pi bond, but then you reform it, and you lose the leaving group like that, okay? Now, technically, again, it's not shown in our textbook, but it'll give you the right answer in a hurry. Let me show you. So if we draw a reaction arrow like that, let's try and draw what this is going to look like. So look, I'm thinking about this molecule here. So I'm going to draw it like this. There's our ethyl ester. Now, what's going to be left from this molecule? The only part that's going to be left is what I'm highlighting in yellow here. Okay, the ethyl or the ethoxy group is going to be gone. So I'm going to make a bond between this carbon that I'm highlighting in green and this carbon that I'm highlighting in blue. Okay, so I'm going to make a bond right here, and that's to the carbon that's highlighted in blue. Well, what's attached to that carbon that's highlighted in blue? It's got a carbonyl attached to it, and then it has a methylene, and then it's got an aromatic ring, and that's the product right there. That's the product of your Claisen condensation reaction. Okay, give me a thumbs up if you follow me on that a little bit, even if you're with me only halfway. Cha? No? Okay, cool. Yeah, so that's my shortcut for doing it. You don't have to do it that way. I mean, students have all kinds of different ways that they like to do things. I'll show you another way that some of my students like to do this. Is what they'll do is this, and I've seen many students do this over the years, is they'll draw the enolate on the other molecule like this, okay? So here's my enolate, here's my non-enolized form, okay? And then they kind of, you know, bring these two together, and they say, well, the bond that's going to be formed is going to be between the enolate carbon, right? And the other carbon involved in that bond is going to be the carbon on the carbonyl of the non-enolized form. Okay, like that. And so if you draw the product out, it's going to look like this. And you kind of have to rotate this bond here in order to have space. Otherwise, the structure just looks kind of goofy. And we try to draw the neatest structures we can, or at least I try to. So we start by drawing this. There we go. Then we have a bond. We have our beta-keto. So there's our beta-keto. And then what's attached to it? All I have left to draw is all of this spinach here, and then I'm done. So I've got a methylene, okay? And then off of that methylene, I've got a methine. And then off of that methine, I've got two ethyl groups, kind of like that. And there you go. That's the product of the Claisen condensation. And that's Mr. Dion's shortcut. Again, I don't have every skill builder in the book memorized, but he probably shows you the exact same type of strategy. Okay, so Claisen condensation is just a nucleophilic acyl substitution. Again, if you want to try drawing my curved arrows here, you draw the nucleophilic attack, draw it a little neater, nucleophilic attack, loss of leaving group, and then you can put this in here. You don't have to do it, but either way, you're going to end up with the right answer in your Claisen condensation. So remember, when you do a Claisen condensation in a molecule that makes a cyclic beta-ketoester, that's the Dieckmann cyclization. So let's take a look at question 21.26. It says, identify the reagents that you would use to produce each of the following compounds using a Claisen condensation. And you notice, you can tell right away, I mean, just by looking at this molecule, with even limited experience in organic chemistry, you'd be able to tell that this is made from two different esters, isn't it, right? So here's the way I like to do it. Here's my alpha carbon. Here's my beta-ketoester. I'm going to break that bond. And in terms of my retrosynthesis, I would be starting with this ester. Okay, I need this ethyl ester. And then my other ester is going to be this one here. Okay, there you go. So the one that I need to form the enolate on is going to be the first one that I drew. I didn't give myself enough space, but I need to make the enolate on this guy. Okay, now how am I going to do this? Now I told you that whenever we do a when we do a crossed Claisen, because that's what this is. This is these are crossed Claisens, crossed Claisen reactions. Okay. Whenever we want to do a crossed Claisen, he always uses LDA. Okay, so what does that mean? It means I'm going to start out with the non-enolized form of this. So this will be my ester. I'll write it like this. The first thing he's going to do is treat it with LDA. So I'll write that down, LDA. The second thing he's going to do is treat it with the other ester. So I'm going to write a shorthand form here. So this is called ethyl benzoate. And then, of course, in the third step, since I end up with that doubly stabilized enolate, right, because there's an acidic proton here in the last step, I have to treat it with aqueous acid, so H3O plus, like that. And that's going to give me the product. Okay, so there's the answer for that one. I'm going to delete my retrosynthesis just to make some room on here. There we go, and I'll move this one up here. And the next one, we're going to try the exact same thing again. Look, we've got our alpha carbon here. There's our beta keto. We're going to break this bond here. So for our retrosynthesis, that means that we're going to have to start with this ester. Remember, if this is an ethyl ester, that means that this has to be an ethyl ester. And I'm going to start it, hey, with the same compound I did before, which is ethyl propanoate. And I need to make the enolate of it. So there you go. There's my retrosynthesis done. So I'm going to delete that, and I'm going to start over and write down what my reaction conditions are going to look like. Let's see. So I'm going to start with this ester, so ethyl propanoate. In the first step, I'm going to treat it with lithium diisopropylamide. In the second step, I'm going to treat it with the necessary ester. So it's going to be this ester here, like that. And then in the last step, we treat it with aqueous acid, and that's going to give us the desired product. And there we go. Hot dog, we have a wiener. Just like that. Give me a thumbs up if you follow me on that one. I know that it's really kind of difficult over Microsoft Teams to interact. You know, in some of these questions, it's harder for me to ask. It's not like an SN2 reaction or something where I can just, you know, say, where's the electrophilic carbon and things like that. Does everybody follow me on this, or are there any questions about that? Is anybody there? Because the next one, we're going to turn up the heat a little bit, like the old frog in boiling water analogy. All right, so let's turn up the heat a little bit, and let's take a look at this one here, because now we want to take a look at it thanks you guys. We want to take a look at a Dieckmann cyclization, okay? And I actually want to try and draw the mechanism here. It says predict the product with the Dieckmann cyclization that occurs when each of the following compounds. So there's only one of them, and let's try drawing the mechanism. Why not? You know, this is the land of the free. So let's take this compound here. I mean, after I said I was going to draw the mechanism, why don't we just draw the enolate? So, right, because we have two ethyl esters. There's one here and there's one here. They're both in the same molecule. But why don't we just draw the enolate to start with, and let's try the curved arrows. So we're going to do a nucleophilic attack like this. I'm serious, you guys. If you just draw the loss of leaving group like that, you end up with the right compound. Okay, you're going to end up with the right structure. Okay, it's just technically you'd have to put this in here to show that the pi bond is breaking to form the tetrahedral intermediate. Then you lose the leaving group. Well, let's look at, and this is going to require some careful carbon counting. So we end up with the aromatic ring. Now, how many atoms? Can anybody tell me how many atoms are going to be in the second ring up here? Is it 6 or 5? How many atoms will be totally in the new ring we're forming? Because we're forming a ring that's going to be attached to this one in the Dieckmann cyclization. Could anybody tell me? If you're not sure, look, here's my carbon. Okay, that's going to be the nucleophile. 1, 2, 3, 4, 5. And there's the carbon, that's the electrophile. So I'm forming a 5-membered ring. So we can just start by drawing 1, 2, 3, 4, 5. There's a 5-membered ring, like that. Okay. If I number the carbons, maybe that'll help. If I call this 1, 2, maybe I'll start from one side. I'll go like this. 1, 2, 3, 4, 5. So that means this would be 4 and 5. This would be carbon number 1, right? Because that's the bond you're forming is between carbon number 1 and number 5. Then we have number 2 and number 3. So what's going to be on carbon number 1 would be the carbonyl, okay? And what's going to be on number 5 is going to be the ethyl ester, all that over here. Okay, and there's the product of your Dieckmann cyclization. You end up with, look, a Beta-Ketoester. I'm going to delete the numbers now. Okay, so you have, look, you have your ester, you have your alpha carbon and your beta carbon. So you end up with a Beta-Ketoester. Okay, and we made a 5-membered ring. There you go. So there's a Dieckmann cyclization. Let's try, is there another one? Yeah, I knew there's another one in here. So let's try the same thing again. It just requires a little bit of you know, a little bit of carbon counting here. So again, this was what? The first step was sodium ethoxide, right? And then the second step is aqueous acid. Look, so let's go over the next one, maybe even a little slower, okay? So look, you're treating this with sodium ethoxide. Sodium ethoxide. So the ethoxide is a good base. You've got an acidic proton here, right? That's an alpha proton. I know there's one here. You could pull off either one. It doesn't matter. But you're going to pull that off to make an enolate. So let's draw the enolate. Why did I pick such a big molecule? I don't know. We're going to end up with this enolate. So there we go. So here is our enolate, like that. Okay, so now we have a good nucleophile, right? Our enolate is going to act as a nucleophile. This carbon is going to be the electrophilic center. So we're going to do a nucleophilic attack like this. Okay, we're going to end up with a tetrahedral intermediate. So let's draw what that tetrahedral intermediate is going to look like. It's going to look like this. So how many carbons are in our ring? Look, we've got 1, 2, 3, 4, 5, 6. I add an extra carbon. No, I did add an extra carbon. I was like, that's not right. 1, 2, 3, 4, 5, 6. So we have a 6-membered ring. So let's draw the 6-membered ring like this. Okay. We could number the carbons. Look, I'll call this one carbon number 1, 2, 3, 4, 5, 6. We'll call this carbon number 1, 2, 3, 4, 5, 6. So on carbon number 1, I've still got my ethyl ester. On carbon number 3, I've got a geminal dimethyl. I don't want to leave that guy out. And then on carbon number 6, I'm going to have my tetrahedral intermediate. So I'm going to have my oxygen, right, with my negative charge, and then I have my ethoxy group down here. So what's going to happen next is the loss of leaving group. So I'm going to lose my leaving group. I eject ethoxide. Then I'm going to end up with this, which looks like the final product, but it's not. I end up with a beta-Ketoester. Okay, so here's my ethyl ester. Here's my geminal dimethyl, right? This is, if you look at this molecule, this is your alpha carbon. There's a beta-Ketoester, but it's not done technically, is it? Right, because you're in a strong acidic solution, or sorry, basic solution. So that means another molecule of the ethoxide is going to rip off this proton, right, to make the doubly stabilized enolate. So we end up with this. And I'm kind of running out of space here, but you'll follow me here. So we end up with this, and we end up with this, and we have our negative charge here. Now, again, everybody here should be able to draw both resonance structures here for this compound. But what's going to happen at the very end is that you're going to throw in some acid, right? H3O plus. So if I want to be correct here, we'll draw the whole Lewis structure like that. And then we're going to do a proton transfer. And then you end up with the final product. Now, again, I'm kind of running out of room here, but I'll try to draw the final product, which was the beta-Ketoester we had from the get-go. And there we go. And there is the product of our Claisen condensation. When we form a ring, it's called a Dieckmann cyclization. Give me a thumbs up if you follow me on that mechanism. Again, it's a 2-step process. The first step is treating it with sodium ethoxide. The second step is treating it with aqueous acid at the end. Did everybody follow me on that? The Dieckmann cyclization, a cool reaction. It's a Claisen condensation, except it's intramolecular. Awesome. Yes. Excellent. I did a job interview in 2007. I went into this guy's office, and that was one of the first things he asked me was with the Dieckmann, or he asked me if I could draw the mechanism, which of course I could. But then he just said, you know the name of that reaction? You remember that from, organic chemistry in university? And I said, yeah, I do. It's the Dieckmann cyclization. I haven't thought about it since, but I do remember it. Anyhow, with that in mind, let's turn our attention to 21.5. There's only a couple of sections left in chapter 21. In terms of new chemistry, it says here that the alpha position can be alkylated when enolate is treated with an alkyl halide. And if I was to ask anybody here, if I said, look, you guys, here's a new reaction, I'm not going to show you any mechanism, I guarantee you that everybody would be able to figure this mechanism out, wouldn't they? They'd all say, well, LDA is a poor nucleophile, but it's a very good base. I've got alpha protons here, so I could draw my LDA molecule. Try to draw as quickly as I can here. So there's LDA. I left it the lithium, but whatever. Anyhow, you'd pull that off, and you'd end up with what? You'd end up with this enolate. And then the enolate is going to attack your alkyl halide in an SN2 reaction. Well, everybody here knows what the limitations of an SN2 reaction are. An SN2 reaction works best with a methyl halide or a primary alkyl halide. So again, the typical SN2 restrictions apply. If you have a secondary or tertiary alkyl halide, you're going to get mostly E2, okay? With a tertiary, you get all E2, and with a secondary, you get mostly E2. So what else is happening here is that it says the aldol reaction also competes with the desired alkylation, so that's why we have to use a strong base like LDA. Right? If you think about it, if you were to just take this ketone like I had on the last page, okay, if you were to take this and you just treated this with, sodium methoxide, let's say, well, in that case, you'd get an aldol addition, right? And if you treated it with sodium methoxide, yeah, you'd end up with you'd end up with a mess in that case. So it's not going to be a very useful reaction. So that's why we have to use something like LDA, because then we get complete, total deprotonation like that. Also, what about regioselectivity? What if I have an unsymmetrical ketone, right? What if I had something like this? Let's say I had, 1-methyl cyclohexanone. Well, then there's two types of alpha protons. There's these ones here, and then there's these ones there. I mean, if you treat it with a base, which one is going to be pulled off? Well, that's going to depend on the base that you use. So the next slide is going to cover that in detail. So it says here, the regioselectivity of that unsymmetrical ketone, we get two possible enolates. We get the most substituted enolate, right? It's the one where the double bond has the most substituents on it. You can see the double bond has a total of 1, 2, 3, 4 substituents. Okay, 4 substituents. Whereas if I was to rip off the other alpha proton, right, then my double bond only has 1, 2, 3 substituents, right? It's also got a hydrogen, which doesn't count as a substituent. And so the way that we differentiate between these is we call the one on the right the kinetic enolate, because it forms faster, right? Because the proton that you have to rip off isn't sterically hindered, right? So it's going to occur a little bit faster, even though it's less stable. Its activation energy is going to be lower. And if we pull off this proton in red, we end up with what's called the thermodynamic product, and that is the more stable enolate. Now, if we look at a comparison of the two pathways that result in the formation of those two enolates, you can see that the activation energy for the formation of the kinetic enolate is smaller, and therefore this reaction is going to take place faster, right? Oops, that's even too high, okay? Here's our activation energy. So this one is going to occur faster. That's why we call it the kinetic enolate. But it's higher in potential energy. It's not as stable as the thermodynamic enolate. So what does that mean? Okay, what does that mean? How do we control this, deprotonation so that we get either the kinetic or the thermodynamic enolate? Well, what we do is this, okay? The kinetic enolate is going to be favored by irreversible conditions. You just rip off a proton at low temperature, and there's no driving force to make the thermodynamic product. So in that case, you would use LDA at low temperature. Now, if you're wondering why it's minus 78 degrees Celsius, why isn't it minus 80 degrees Celsius? It's because when you have minus 78 degrees Celsius, this is when we mix carbon dioxide, solid carbon dioxide, which is dry ice. We mix that with solvents like isopropanol, so isopropyl alcohol. So it's dry ice and isopropanol. It's very commonly used by organic chemists to make this very cold bath, so to speak, that you can put your reaction flask in. So that's where this ubiquitous minus 78 comes from. Anyhow, so LDA at minus 78 is going to deprotonate the proton that is less sterically hindered. Then we get what we call the kinetic product. So we would call this the kinetic product. Okay, and if we use a non-polarizable base like sodium hydride at room temperature, 25 degrees Celsius, then we're going to end up with the thermodynamic product. So the thermodynamic product like that. And so you have to have these things memorized. Let's take that knowledge and apply it to some practice problems. Here, if we're taking this compound, so this is cyclohexyl methyl ketone, is a perfectly acceptable name for this compound. First, we're treating it with LDA in minus 78 degrees Celsius. So I have the proton in blue and the proton in red. Could anybody tell me which one of these protons would be the one ripped off by LDA at minus 78? Would it be the blue proton or the red proton? Yeah, absolutely, Skylar. It's going to be the red proton. Why? Because it's less sterically hindered. So we're going to pull this proton off. I'm going to draw the intermediate that would be formed. So this is the enolate, and it doesn't ask you to draw this, but hey, it's just fun. So you end up with this intermediate, and then when you treat that with with your methyl iodomethane or methyl iodide, whatever, same thing. So let's draw the methyl iodide. That's just going to do an SN2 reaction. So nucleophilic attack, loss of leaving group, and that's going to give us our product. So all we're doing is adding another carbon to the molecule. Boom, boom. There you go. Nothing more than that. So kind of a cool reaction, though, just to add an extra carbon, right? Whenever you can add a carbon or make a new carbon-carbon bond in organic chemistry, that's going to make you kind of famous, isn't it? All right, the next one is using sodium hydride. So this time, if I have the blue proton, oops, that's not blue. That's right. If I have the red proton, which is the less hindered proton, and I have the blue proton, that's the more hindered proton. Well, since I'm using sodium hydride, and it doesn't say anything about the temperature, so we can assume that it's at 25 degrees Celsius. It doesn't indicate anything otherwise, so we would assume it's around room temperature. That means I'm going to form the thermodynamic enolate, which is going to look like this. I'm just going to draw it a little differently this time with the negative charge up on the oxygen. It doesn't matter. Next, I'm treating it with this compound, which is called benzyl bromide. So this is benzyl bromide. The reason I'm telling you that it's called benzyl bromide is just a very common electrophile in organic chemistry. So what's that going to look like? Let me draw the benzyl bromide here. So I'm going to draw it like this to show the methylene so that I can draw an appropriate mechanism. So I'm going to get my nucleophilic attack, loss of leaving group like that. And I'm going to end up with the final product, which is going to have this 5-membered ring. I've got a methyl group here, methylene, and then I've got my aromatic ring. It's not the most pretty aromatic ring, but it'll do like that. If you really don't want to draw the aromatic ring, you can just write the abbreviation phenyl like that. And there you go. So now you've learned about kinetic enolates. So that was the first one, was kinetic enolate formation. And the next one dealt with thermodynamic enolate formation, dynamic, okay? And we've learned about the conditions that are required to make the kinetic enolate, thermodynamic enolate, and we saw how we can do alpha alkylation. Well, the good news is that there's even more cool ways to do alkylation at the alpha position of a carbonyl compound. Let me show you some other things that we can do here. We can do what's called the Malonic ester synthesis. You guys remember malonic acid? You remember, oh my stars, go away. That's what I taught you. So oxalic acid has 2 carbons. Malonic acid is this. It's got 3 carbons. So this is, oops, that's not very good. This is malonic acid. You would have learned it in chapter 20. So if we make a malonic ester, we basically take these 2 hydrogens and we replace them with ethyl or methyl groups, but we usually use ethyl groups, okay, for everything in chemistry 3111. So we end up with this ester here, and it's called diethyl melonate. So this compound here, let me write the structure over here. So we make the ethyl ester, and this is called diethyl malonate. And you can see that it's got a couple of very acidic protons in here, doesn't it? And diethyl malonate. So here's what you can do with a malonic ester synthesis. now that I've covered what malonic acid and what diethyl melonate is, you can actually take an alkyl halide, just your regular old run-of-the-mill alkyl halide, and you can actually add a methylene and a carboxyl. Okay, so you actually end up adding 2 carbons, and on the second carbon, it's a carboxylic acid. So it's kind of a cool reaction, and the mechanism is, very, very reasonable, I would say. It's usually something that students don't struggle with. So the first step is to treat your diethyl melonate, which can be purchased from a chemical supplier. You don't have to make it. You just treat it with sodium methoxide, which is also commercially available. You can buy it anywhere from any chemical supplier. So you do that, and you end up with that doubly stabilized enolate. Okay, so that's your first step. But then what happens is that doubly stabilized enolate can act as a nucleophile, and your alkyl halide can act as an electrophile. So then you've got your nucleophilic attack, you've got your loss of leaving group, and what all you end up doing is putting an R group in between the 2 ethyl ester groups. Okay, so that's all you're doing, is you kind of get like this double alpha carbon, if you will, and you're putting an R group there. And if you're wondering, hey, Mr. Dion, there's a second acidic proton here. Could I put another R group there? Yes, you can, and we'll look at examples of that. Okay, so all you've done is add your R group there. Now check this out. If you treat this compound, okay, which is redrawn here, with acid, and it doesn't say anything about heat, but let's say you heat it up a little bit, what are you going to do? You're going to hydrolyze both of those esters to a dicarboxylic acid. But the thing is, this is unstable. Okay, I'll put here unstable. It actually falls apart, right? And the way that it falls apart is this, okay, is you end up losing one of the carboxyls. It just goes away in this very cool cyclic mechanism down here. I'm not going to ask you the mechanism, but it's not a very difficult mechanism, is it? It's 3 arrows, okay? All you have to do is rotate this carbon-carbon bond so that you can put the carboxyl group in this orientation, and then you do the loss of carbon dioxide, and you end up with this intermediate, which undergoes a tautomerization. So this is called an enol, right? Or sometimes this is called an enediol because you've got 2 hydroxyl groups on it. But anyhow, you end up with this compound which undergoes tautomerization, and you produce a carboxylic acid. So there you go. That's the whole thing. So how many steps overall is the malonic ester synthesis, right? The total thing is 3 steps. Let me show you. Overall, you start with diethyl melonate. So that's this compound here, diethyl melonate. You treat it with sodium methoxide in ethanol, right, to avoid transesterification. Okay, that removes the acidic proton. You end up with the doubly stabilized enolate. It does an SN2 with your alkyl halide, and then you blow the whole thing apart with acid like that. And what you're adding, right, here you had 1 carbon attached to your aromatic ring. That's this one here. What you do is you add 1, 2 carbons, and the second one has a carboxyl group on it like that. Now, like I told you, the diethyl melonate, since it's got 2 acidic protons, right, count them, 1, 2, you can rip off each one of those, and it can be dialkylated. The order here is not important, okay? You could put 1 R group first, the other one second, doesn't matter. But then when you blow that apart, what do you end up with? You end up with a carbon and a second carbon that's a carboxyl, and now you've got 2 R groups. So instead of being a CH2 or a methylene like it is here, now it's a methyne. Okay, so that's the malonic ester synthesis, a very cool kind of tsatsi reaction. Well, what I'd like to do now is to take a quick break, and I want us to think about question 21.31, and we're going to come back and take a look at it. All right, it says propose rather an efficient synthesis for each of the following compounds using malonic ester synthesis. So that means that this part of the molecule here is going to come from our diethyl melonate, right? That means that this part of the molecule here is going to come from our diethyl melonate. So I'd like everybody to give this one a shot.